So thank you for joining today's session. My name is Nigel Douglas. I work at a company called Tigera, and we're responsible for an open source project called Calico. Today's session will cover cloud native application protection for specifically Rancher RKE and RKE2 clusters using Calico. So with that, I'll give an introduction as to what Project Calico is, how we built our base security using the open source project with its network policy capabilities. I'll cover what CNAP is, so container networking application protection, and then I'll provide kind of centralized security posture for those clusters using these CNAP capabilities. I'll provide some closing notes as well and just additional resources regarding our topic. So yeah, I'm based in Cork in Ireland. I've worked as a solutions architect at Tigera, working with all sorts of distributions of Kubernetes. Since Calico usually comes as a kind of a default CNI implementation, or at least it comes as a supported implementation in those different providers. I've had the opportunity of working with RKE2, RKE instances of Rancher, as well as installing in Rancher desktop in my own lab. So I really enjoyed working with different distributions of Kubernetes, pretty much anything Kubernetes in cloud I enjoy working with. So yeah, you can contact me directly via my email or via the Calico Slack user group. It's free to join. So with that, yeah, Project Calico, it's a widely adopted open source project. Main reasons for doing so is it works across multiple different data planes. The default implementation uses standard Linux, so kubeproxy and IP tables. If you have a use case for eBBF, let's say, for high scalability, or maybe it's around features like XTP, for preventing denial of service type attacks, then you might want to use eBBF data plane, of which we support that. For Windows workloads, we support Windows HNS, and then for specific telco use cases, there's VPP data plane as well. So it's supported in a bunch of different distributions, pretty much everything. It's cool that it supports different data planes for different use cases, and from a performance standpoint, it's highly performant. If we're looking at independent benchmarks, so not from my own perspective, Calico usually comes out favorably. The reason for that is, yes, there's encapsulation methods like IP and VXLAN, but if you want to avoid encapsulation overhead, we have BGP routing. This also provides scalability options, so high scalability, when we can interact with our underlying IP fabric, but also this tends to lead to minimal overhead, that reduces costs, and it's just good overall if you can make use of that. Also, our security policy or network policy definition is, it's a extension of what's already capable in the default Kubernetes network policy implementation. So there's a lot of use cases for Calico, extending to legacy VMs, whether it be, extending to underlying networking infrastructure other than what's going on within the cluster. Most of what we'll cover today will apply in some shape or form to policy. So we'll talk about CNAP, how CNAP applies, so what it is, but most importantly, how we can take these different technologies and run them against our existing policy framework. The screenshot you can see in the top right corner uses the standard Kubernetes network policy definition. So you can tell that in the API version, networking.kas.io. Calico's one will be something like projectcalico.org version 3. In this case, why we use policy is because by default in Kubernetes, the network model is flat. So essentially all pods can freely talk to one another without the use of NAT, so network address translation. This inherently doesn't provide any security posture. In fact, it's incredibly insecure. It's nice because when you deploy your apps, they can talk to each other and things work. But it's hard to secure. One of the main reasons is because, well, Kubernetes is a orchestrator, so it's responsible for orchestrating containers as pods within a cluster. So when you scale up or down, pods tend to die. So this terminology of being ephemeral, they get killed and get recreated as part of the deployment process. So as a result, a pod actually does have its own IP, but doesn't tend to be very long-lived. If it dies and gets recreated, it doesn't come back with the same IP address. So these pods themselves are non-deterministic. They usually don't need to be in any specific network namespace. And as a result, also the IPs don't need to be assigned. So it's very hard to say we're going to target these workloads based on name or location. Instead, we want to have something fixed. So again, unlike traditional firewalls, which do tend to be based on IP, that won't really apply here. We want to do something that's more static. So you can see from the actual picture in the top right corner, it's using things like match label selectors. So in your deployment at the highest level, you can assign arbitrary labels to workloads and then target those labels within policy. So whether you're using the Kubernetes definition or using our standard network policy API, you can target something static like a label to a workload. And we'll come through all this in a while. So yeah, building the base security, it's traditionally done, via policy. But, if we didn't have even policy in place, you can see that the attack surface is quite large. Workloads can freely talk to each other. Maybe we have a multi-cloud setup. And in this case, you have very little visibility without going into each cloud environment to see what is the posture and configuration of our virtual firewall, essentially how we control what workloads are allowed to talk to each other. The risk of lateral movement in any given cluster or even outside of a cluster is, potentially quite, large. I mean, they can talk to external resource if you open up ports and protocols outside of the cluster. Also, from a view of vulnerabilities, you tend not to know what is unusual behavior because, like I say, you don't have a long-lived pod to say, okay, based on historical behavior, it did this and something else, because we're not targeting it based on IP or name. So you want to have some way of kind of having Kubernetes native constructs to understand what is that static service, irrespective of changes made to it, and be able to understand what is the unusual change in behavior. So again, from a compliance standpoint, it's really hard to lock down and apply compliance controls if things are changing. But also if a threat does occur, and let's say you're late to identify it, the cost of the zero-day attack is generally quite large. You see that with ransomware attacks today, or any kind of banking threat like Emotet in traditional networks. But also the risk of non-compliance also leads to its own inherent costs. Remediating the process, the actual cluster is somewhat complex, but also it takes time away from developers that otherwise should be investing their time in innovation. So yeah, to give you an idea of what cloud native application attack vectors look like, people tend to write the code that's written or the images that are deployed into the environment is in the build time. From here, there might be misconfigurations on those images. Again, whether known or not known by the developer, this can happen. So misconfigurations in the code itself may lead to a vulnerability, or it's just a bad image that was brought in. So from a deploy time perspective, there's also misconfigurations that can occur when it's going to be brought into the environment itself. So again, we can secure the controls both from the build time through to runtime. So this also goes through the deploy time. But assuming you didn't have any of this, like in open source Calico, it doesn't do, image registry scanning. This is part of our enterprise solution. So just for total transparency here, there's tools you could use for runtime, build time scanning. This should give you a kind of a general view of the whole landscape. So at the very earliest point, you should be scanning images for potential vulnerabilities or just unusual changes that shouldn't have happened from a developer's perspective. But assuming a bad image has been brought into our cluster, this is very much the runtime. So what's going on within the cluster? So there's a malware that's introduced. How do you tell it's different versus all the other pods that are running your cluster? They might all be in a generic default network namespace. The names all look pretty much the same. And, again, because they're not long lived, we don't know that this behavior is any different to another time. How do we know it's expected behavior that more traffic is generated or not? So with that, like the potential data exfiltration attempts, can quite easily be behaved here because or be performed here because pods can freely talk to one another. So in that scenario, without policy or any kind of restrictions in place, you can talk to any other pod. So if you find a pod that's let's say a backend database with sensitive data, how do you protect it? And if it's not protected, what stops then the rogue attacker from taking sensitive data that's being transmitted in plain text and communicating with some kind of command and control server outside the cluster? So you see here with services like Twilio and Salesforce and Graph, if we can open these up via, like, let's say an egress gateway, we create a routable fixed IP on a workload to talk to those external services, or we create a, how do we secure it? So like there's different ways we can go about this. A nice way on egress in our enterprise solution is to use DNS policy, target a specific API and only allow, say, port 443 over TCP to talk to that external, fully qualified domain like api.twilio.com. And again, any other pod that isn't targeted as the allow rule is otherwise not allowed to talk to those external services. So you can kind of lock it down that way. Same rules apply to unauthorized access to legacy VMs. I may have said this already, but you can run our Felix agent on external, bare metal VMs as well, outside of the nodes within the cluster. So if we're allowing connection to, legacy systems, you also want to prevent that integration or that traffic from being able to communicate with those external services. So we can integrate with them. It's cool that we have firewall integrations. We have this universal firewall, the egress gateway, but you also need to use policy to lock down what traffic exactly can talk to those external services. In the case of a zero-day threat, it's hard to see what the difference is between that and any other threat, especially or any other workload, because the traffic all looks the same if you're not aggregating and getting some kind of alerting system in place. So we can do that in our enterprise solution. And then again, threats of malware, ransomware, like what they can do, where they can do it, we have little control without policy. So policy should be the place to start, but we have other capabilities to lock down and prevent, and we'll go through all those later. So the first thing you would probably want to do is create some kind of default deny. So you can see in this scenario, the policy, I don't know why I needed the screenshot to show it in the shell. Basically, you can see it the same fine in the top left corner. But the policy itself in this case is, you can see we allow some service like, for say kube system or Calico system, or basically we're saying target anything that is not in kube system and Calico system. So you can see we use Boolean logic here in policy, which is really nice. It means you can quite easily customize your policy to a great extent. So you can say and or operators. But in this case on the egress, we're whitelisting. So you can see the action allow for UDP traffic to things that are labeled k8s app equals kube DNS, which is essentially core DNS or DNS function. For DNS, we want to allow port 53 because that's what's being used for DNS traffic. So whitelist anything that's DNS, anything else, drop it, That's one way of doing it. And to see your policy actually working, you can say kubectl get policy, that global network policy. If it's a global policy, to know if it's a global policy or a namespace code network policy, you can define that within the kind in the second line at the top of the policy. So it's kind network policy if it's a namespace code. If it's going to apply to the whole cluster, it's global network policy. Global network policy makes perfect sense for something like core DNS, because all the pods and all the different network namespaces are going to rely on core DNS. And with the Kubernetes network policy definition, you would need to do this on a per network namespace level. There is no global network policy, and that's otherwise pretty hard to manage. Also nice about the enterprise UI is once you build a policy, you can actually see it inside a web UI. So we have Elasticsearch UI. We use Prometheus for metric scraping to populate the view to see if packets are getting allowed or denied as per policy. So from a compliance perspective, we know policy is working, and we know if there's something going wrong, like it goes red and we see traffic getting denied, we can investigate it further via our web UI. So let's say we've introduced a real world test application. You see the example here where if I said kubectl get pods in that namespace with -o wide to see what are the additional statistics or information, I can see that there's an IP assigned to the different pods. When it's container creating, obviously it doesn't have an IP, and when it eventually got created, it was assigned an IP from IPAM. They're all running on the same node. This was actually in Rancher desktop, which is cool to use, personally speaking. But the best one to use here is because IPs are going to change. There's no point us focusing on the IP. Instead, you use it actually should be --show labels in the command I'm showing there, but that will show you the labels assigned to your pods. Once you know the labels assigned to your pods, you can create something like you see here, like a zone-based architecture. This will apply for Calico open source the same way it works for enterprise. There's only a few little differences here in regards to tiering, and I'll talk about that in a second. But basically, we want to secure a backend database to make sure it can't have communication with public internet. So we create a first policy on the left, and it's saying anything with the FW-zone label, which is equal to DMZ, which is the key pair value match. It's allowing traffic from an IP set, a list of IPs that is referenced with the label IP set equals internal. You could also just use the CIDR match if you wanted in this case. Then it's allowing it egress to pods with the labels of firewall zone is trusted, so it can talk down into the trusted zone, so egress out to trusted, or anything with app equals logging. Once that occurs, then that same traffic is gone from public internet through this DMZ, demilitarized zone, and then it can go to the trusted zone if it matches those conditions. Then the trusted zone is basically saying anything with the label FW zone trusted, allow it to following ingress egress actions. So it can receive ingress from DMZ or from the database, which is in the lower zone. So this is kind of an arbitrary zone system we're creating, but it can egress out to, so it can talk to, again, these are all allow rules, to trusted or the restricted. So into its own zone, there might be more than one pod in the same zone with the same label. So you can say it can egress out 2 pods in the same zone or into the lower zone. And from there, then you have the restricted zone, which is basically saying I'm only allowing ingress from the approved pods in the trusted, or if it's in the same zone, restricted. Anything else, I'm allowing egress out, because the only way it can get to the higher level to public internet is through the above zones. Once you've created this zone-based architecture, even though in itself is incredibly secure, because you're only allowing it based on the labels you approve, you could create a default deny at the bottom, which basically says anything that otherwise isn't, matched in this zone-based architecture, let's say a new pod that might get introduced, a rogue attack wrap, it will get dropped. Now, the only difference between this in the enterprise view and the open source one, as you can see here, is there's a concept of tiering in their enterprise or cloud solution. So this ability to logically put policies into tiers. In open source, there's no graphical UI, so there's no tiering. So I just scratched out the specification for tier equals whatever tier name. And the same applies to policy name. We have a syntax which is basically tier.policy name. So removing the tier, then it's just policy name is referenced in the policy, and that should work fine. With that, I removed the example there, and this policy should work fine in open source Calico, no problem. So once you have your policy created, you should be good to target those workloads. Now that's what we can do with open source Calico. We can build policies to lock down what our workloads can and can't talk to other workloads, but there are more capabilities that apply to CNAP. So fundamentally, CNAP will ask for end-to-end security, not just in runtime. So the first part is you want to have, for instance, image assurance. So image assurance is the ability to continuously assess first and third-party images for vulnerabilities. What I mean by vulnerabilities are known flaws, let's say things that could be compromised by an attacker, so they can make use of that vulnerability. So what we can do is we can schedule scans within our UI to basically check for any changes, or if they have a bad image. And then again, using admission control, prevent that from getting brought into the environment. So essentially define and manage the exceptions of what you do and don't allow into your environment. From there, there's the compliance you have to consider. So open source Calico, like I say, no graphical UI, no reporting capabilities. It's perfect for locking down what workloads can talk to each other, but demonstrating to an auditor that you're actually meeting that compliance standard is difficult. So what we can do is we can schedule reports based on the label concept as well to the network traffic. So like I mentioned, traditional tools don't work really well when it comes to enforcing compliance in Kubernetes, because they don't know what changes occur to workloads, because again, if it's based on IP, those are going to change. Since we can say target anything with PCI equals true is the label selector match, then it's very easy for us to build an audit report to say, show me policies that are currently applying to anything with PCI equals true as a workload. And this can apply not just to PCI, but you could apply similar, because labels are arbitrary. So you could build something arbitrary around HIPAA compliance for healthcare, GDPR for European businesses, or SOC 2 compliance, or platform providers, or FIPS. So there's all these different compliance standards you have to meet. And being able to customize your compliance reports is also incredibly important. And being able to use WireGuard, if I haven't mentioned this already, is a way to encrypt traffic in transit to make sure it's not being sent in plain text. An auditor wants to be able to prove that WireGuard is being, or an encryption method is being used to make sure you're not transmitting plain text, especially when it's payment details in case of PCI. And I've got a separate session on that at SUSECON as well about PCI compliance. So with that, runtime threat defense, we talked about this. You can use policy to lock down what workloads can and can't talk to others. But as part of the regulatory compliance standards themselves, they'll often ask for a bit more than just, using policy. You want to have a bit more intelligence about what's going on in your environment. So what we can do is we can subscribe to IP feeds associated with known, bad actors, like for instance, a block list that could be coming from a security vendor. We can subscribe to it via a custom resource called a global threat feed. Then that becomes an IP set or a network set, like you can see in the screenshot on the right side. So it's just a long list of IPs inside or matches. And then at the top of that screenshot, you can see it's labeled the network set with threat feed equals Fyodo. So then I can use the same policy to say deny egress traffic to threat feed equals Fyodo. And the same can be said for ingress. So you can block traffic to these IP sets, and the responsibility then for managing the IP is really on the security vendor, not so much on Tigera that provide Calico, but on wherever you got that IP feed from. So in the case of Fyodo tracker, it comes from a company called abuse.ch. They're a great team of analysts that check for known botnets or C2 servers. They block them if they're no longer malicious or known to be bad. They'll whitelist them. So as they make the updates, we'll do the default daily check to update that IP feed. And then policy stays static. It just says deny traffic to these known labels. And then all the legwork of updating the feed is really done for you automatically. So that's a really cool case, and we'll show how that's created in a while. From a runtime security, like we have loads of these cool features like intrusion detection, prevention, whether it be through machine learning algorithms. We have zero-day attack prevention through honeypots. So you can essentially create a fake pod in your cluster and call it sensitive database. Assign a template to it so that if a pod tries to probe that pod, triggers an alert and you're notified as an admin that there's unusual behavior. Similarly, we have deep packet inspection. So things like snort signature rules and your own custom list that you want to apply. You can enforce those into rules so that, again, if there's any changes to a workload, it triggers an alert to notify you that there's some security incident. People think of Calico as default, L3, L4, which makes sense, the networking solution. But also we can use Envoy, not as a sidecar like in service mesh. We can actually use it as a daemon set on the nodes. And why this is really nice is, you can collect the L7 stats, so we can get HTTP traffic, application layer traffic, and also apply this to policy to say secure traffic on the application layer, which may remove the need to use a service mesh in some cases. So really nice feature to have, and I'll try and show that as well in the next the code snippets. The last part I'll talk about, and I already talked about this, is you can build policy and certainly deploy at the earliest point. So the policy is code. That's really nice. Like apply to automation systems like your GitHub pipeline, CI/CD pipeline. In the enterprise, it's slightly different to open source in the sense that you have this policy tier. So you can kind of organize a shift left approach of putting a security tier in front of a product tier. And then these higher level security policies, they get read before the tier on the right of it. So essentially get read from top to bottom, left to right. What's also cool, and you can see in the screenshot on the right, is if you're new to policy or there's an incident that occurs and you want to block it or allow it, there's a policy recommendation feature, which in the UI, you just click on recommend, target the workload that's broken. And based on historical traffic, it will say, allow these ports and protocols between these pods based on label. So it has all that context that aggregates. If you wanted to deny to a strange pod that's currently communicating or historically was communicating with, still use recommendation and just swap allow to deny. So it's a really, really cool feature, and it certainly speeds up process of, responding to security incidents. And then the last part there is, if you're integrating with traditional firewalls, we have, egress gateway capability to assign a fixed IP or routable IP to a workload in a given network namespace. And this, again, allows you to leverage existing firewall rules for those pods, like you can see in the screenshot on the right side. So trying to communicate through to services like Salesforce or whatever it be, and go through an existing firewall. The firewall expects a fixed IP. Pods don't have them, like we mentioned earlier. So being able to use egress gateway to create that routable IP means that that fixed IP we can communicate with the static firewall. We also have DNS policy, which doesn't exist in the open source project, but it does certainly exist in our enterprise solution. So this allows you to say, like I mentioned earlier, allow or deny to a fully qualified domain. And then, like I mentioned earlier about network sets, rather than managing these complex CIDR ranges, you can subscribe to the network set itself through threat feed. So if someone else is providing a list of bad IPs, you subscribe to it, and then you have a static policy denying that traffic. Identity-aware microsegmentation kind of makes sense in itself. Is, if we understand the context of the workload based on label, then making policy changes, whether it be cross clusters to different distributions, it's really easy because the same label schema will apply, and then we can dynamically update quickly. We can copy a YAML manifest of the whole cluster, apply it to the other cluster if it has the same pods and same label schema. It's all fairly easy to reproduce. And from a perspective of what's going on within a cluster. We have dynamic graphs. Like I mentioned, it's Elasticsearch UI. Since we're streaming all the data via Fluentd to this UI, we have all the audit, the DNS, the L7 traffic going through here. We can aggregate it, and we have alerts as well. We have all this additional context. So we can easily see where the bottlenecks occur and what traffic's getting denied between workloads in the cluster or outside of the cluster, what communications egress out of the cluster. So you can easily see performance gaps, any incidents, and again, be able to fix issues really quick. So this is brilliant for both application developers, platform teams, security teams. A bunch of teams can use this for, again, meeting compliance as well. If you want to generate a packet capture, you can do it in the UI. Essentially, right-click on a workload in a network namespace. And as you can see from the screenshot, there's an option at the bottom that says initiate packet capture. So you can do a packet capture for, let's say, TCP 443 on workloads that match this label concept. Again, I'll show this code snippets later. That's a really cool feature and certainly better than the alternative, which is to exec into a pod and run TCP dump, which is, even if you don't have the elevated permissions, you need to get that. And then you would need to do it on the per pod level anyway. Whereas here you can schedule it for specific times. Certainly saves a lot of time for teams troubleshooting network related issues. And then the application level observability I mentioned a while ago, being able to do WireGuard encryption as opposed to mutual TLS is grand because it takes us away from the service mesh idea, but we're also collecting the L7 traffic via Envoy. And I'll show those examples in a while. We can use WAF as well, Web Application Firewall, for the application traffic. So centralizing our security posture, I try to put some snippets together. I think I've explained labels already, but if you're not familiar with the concept or need more information about it, it's a key pair value match system. So you can see from the snippet below, it's like key 1 equals value 1 and key 2 equals value 2. It's arbitrary, so you can build it whatever way you want, totally unique. If you want to learn more about it, there's a link to Kubernetes IO on that topic. We talked about the zone-based architecture, really good to use, and it will be applied to multiple different security incidents going forward. Here's a good example of using policy to block the IP feed. We use the CR, custom resource, for global threat feed. In this case, we're basically making a pull request from a HTTP-based URL, and that URL is fyodotracker.abuse.ch, and they've got some text file. So that text file, they're hosting it. What we do is we're making the checking for what is the content of that text file, and then we're converting into another object called a global network set, and that network set has a label of threat feed equals fyodo. You can see that in bold. That's all we really care about, because the rest of it is just going to sit there statically. The label is assigned so that in policy, we can then, you can see, make an egress rule to deny is the action set on the selector threat feed equals fyodo. So in that case, you can block traffic to the known bad list. Similarly, from a packet capture perspective, because there was one thing me visually showing it to you a while ago, but explaining, if you're creating it from the CLI, you can target the labels associated with the pods. Similar to in policy, you say, generate a PCAP file for anything with the label k its app equals nginx in the namespace sample. That's basically it. And this will apply to the pod nginx. From the second example there, you can say, if you wanted to go further and you want to say, okay, look for all matching selectors. I don't care what selector it is in the sample namespace, but filter it for just TCP traffic. I don't want any of that UDP stuff. And you can do it that way. And then if you want to go further, again, you want to get TCP traffic for pods matching certain labels in specific network namespaces, then specify a start and end time. So as you can see there, it uses this RFC 3339 format. So basically it's where it's the year, month, day, and the time is formatted in a certain way. But either way, yeah, those are packet capture jobs, and you can schedule those, and you can be as, broad as you want with those definitions. The alert template is harder for some people to get their head around because, you need to understand the data you're aggregating. But in the web UI, you can essentially go into templates and pick a template for any topic. It could be an example of denial of service prevention, or in this case, I'm showing at the top a lateral movement scenario. You can build one whatever way you want. But I think this is always a good example. If you want to catch someone out for unusual behavior, then basically label your secure workload with something like security equals strict. That's the label we're giving to it. And then basically it's going to trigger alert to tell us, well, based on our flows, we've seen lateral movement where some injected source name pod in a source name destination tried accessing our destination pod, which again, we haven't said which pod it should be, some destination pod and a destination namespace that happen to have the label of security equals strict. So let's say no one should talk to the pod with security equals strict. And if any pod tries to communicate with it, triggers an alert and notifies the admin of it. You could certainly use this in an automation attempt to, isolate a workload for doing unusual behavior, but also at least from an earliest stage, you can notify the admin that there is some unusual behavior in the environment. That's just a generic scenario. And from a WAF scenario, like I say, we can collect the L7 traffic. So by turning on this application layer custom resource saying web application firewall is enabled, then when you want to target a specific service to say this service in this network name, whatever it is, you want to be able to say L7 logging equals true. So essentially you're turning on the L7 traffic for it. If you want to disable it, it's just by saying L7 logging, don't say any value. So basically remove the annotation. In this case, things like cross-site scripting, SQL injection, cookie poisoning, they're all examples of WAF or L7 or at HTTP level attacks. So being able to use WAF, as a way to prevent those leading cause of breaches is really cool as well. So we're securing not just on the network, but also on the application layer. And with that, I'm just going to put some closing notes. There's a lot that I covered, and I hope some of it resonates or it's interesting. I put a repo for if you want to test some of these security cases in a Rancher desktop, essentially like a lab environment that runs in your own desktop, whether it be Windows, Linux, Mac OS. I personally run it on Mac OS. It's brilliant. I was able to test it myself, and you don't have to fork up any costs for infrastructure for testing it in Kubernetes. So I put a GitHub repo for testing some of those security cases. Thanks to the team from SUSE for putting that together. I've also linked to our partner pages for Rancher if you want to learn more about how Calico works with Rancher RKE and RKE2. And if you want to learn more about Calico in general and just get certified in it, then we have the Academy for Tigera, the Calico certified course. It's totally free to sign up, and you get a certification at the end. So hopefully the session was interesting, and have a lovely day.